So, continuing this story, equation 2 is the multiplicity of a single atom in a box where we have specified the macro state by the volume of the box and the total energy of the atom. Okay? So this is the number of states that there are. Remember, multiplicities are very large numbers. That's what we're going to end up with. Now you only got one atom right now, but we'll get to the final answer here soon. B. Now we're going to work our way towards a multi-particle ideal gas. Okay? Well, let's take the next logical step from a multiplicity function for one atom in a box to two atoms in a box. Let's make them, by the way, since we're going to build this up to say maybe we're describing helium gas in the box. So the assumption is that the second atom I'm talking about is the same species as the first one, which in quantum mechanics means they are indistinguishable from each other. That's important. Okay? All right, so now let's suppose that we have n, capital N equals 2 identical atoms. Right? We're going to extend equation 1 to get the multiplicity for this new system. So I'll do this by a series of bullet points. First bullet point, the extension here is going to be just pretty much by common sense. Remember, it's just counting. And so we're just basically, well, we're doubling the number of atoms. Okay? So now, each particle has volume capital V in position space. Sorry, by the way, I'm extending equation 2. Right? Each particle has volume V in position space. So in equation 2, just take the V that you see there in equation 2, and you replace it with V squared. Remember, multiplicities multiply when you have multiple atoms. Remember the two Einstein solids? Okay? Multiplicities multiply. They don't add. They multiply. So the V goes to V squared, not 2V. Okay? All right. What else? Each particle's, I'll say, volume per state in phase space is h bar over 2 cubed, right? Each particle's volume per state in phase space is h bar over 2 cubed. So, in equation 2, where you see an h bar over 2 cubed, we will exchange it with h bar over 2 cubed squared. So cubed times 2 in the exponent, 3 times 2, which is, of course, h bar over 2 to the 6. Okay, so far, just extending equation 2 to what I'm going to have. I have 2 atoms. Now, the next one is a little bit more subtle. How do I deal with specifying the total energy available? Capital U. Remember, that's lurking up here in equation 2 because the radius P of this shell in momentum space depends on U. Okay? So how do we do that when we have a two-particle system? Now remember, the U here is always going to mean the total energy. Total energy. That's always what we're going to mean by U as a macro state property. Total energy. Well, I have 2 atoms with translational kinetic energy. So there I get the total energy by adding. I mean, energy does add. Right? So, the energy constraint. Well, it's really the momentum constraint. Of the two particle system is that, I mean, I could write it as, well, I would write it. U, that's U total, is 1 over 2m times px1 squared plus py1 squared plus pz1 squared plus px2 squared plus py2 squared plus pz2 squared. Right? I mean, you can think of this as u1 plus u2. Right? You can think of it that way. u1 is that plus u2 is that over that. But the u here means u total. So u total is u1 plus u2. Okay? Now another way to write that is that we have to have px1 squared plus py1 squared plus pz1 squared plus px2 squared plus py2 squared plus pz2 squared equal to 2 times the mass of either atom by itself, right? That's the mass of an individual atom, times the total energy. Right? So that would be the total energy of the two atoms. So I will have specified that. And of course I will know the mass of each of the atoms. So this point, the point is this side is fixed. So this sum of squares is fixed in momentum space. And notice now the momentum space is six-dimensional. There are 3 momentum axes for particle 1's momentum and 3 momentum axes for particle 2's momentum. So the momentum space is six-dimensional. Of course, the position space is six-dimensional too, because there's an xyz for particle 1 and an xyz for particle 2. So the phase space is 12-dimensional. Okay? But what I've got right now is a constraint in the six-dimensional momentum space. Okay? And I can still think of that, since that's the sum of the squares of each of the 6 momentum coordinates, that this can be thought of as the radius squared of a sphere in six-dimensional momentum space, right? That's how you would calculate the radius of a sphere in a six-dimensional space. Take the sum of the squares of each of the 6 momentum components. Okay? So the way we often write that, by the way, radius squared of a sphere in six-dimensional momentum space, is I'm just going to kind of use somewhat loose language and describe that as the radius of a momentum 6 sphere. So the point is, right, that I'm limited now in momentum space, right, because this fixes the radius, so I'm limited to a sphere again in momentum space, and I need to figure out how to get the volume of this sphere, because that's the spherical shell, because that's what's available to me, right? The available volume in momentum space of this 2-atom system, but that was what we were calling V sub p, would be the surface area of a 6 sphere with some radius p, where p is again the square root of 2mu times a thickness to this shell, delta p, from the uncertainty principle. That delta p, by the way, is never going to be an important part, but it is technically there. Here's one thing I can tell you about this area. The surface area of a momentum 6 sphere of a certain radius has to have dimensions of the radius to 1 power less than the dimensionality of the space. So that would be p to the 5. Think about it. Think about a sphere in 3-dimensional momentum space. The surface area goes like p squared. Okay. All right, so what we have to now find out is how we calculate this surface area, though. Because the question is, well, what is it, though? What is the surface area of a sphere in 6 dimensions? Well, except I know that it goes like p to the 5th. But what multiplies that? Okay? That's an interesting question. So that's what we're going to look at now. Okay? I'm not really going to do a formal proof of this. I'm just going to kind of show you some steps of the argument. Okay? But at the end, I'm going to show you a formula for calculating the surface area of a d-dimensional sphere. Once you get above 3 dimensions, by the way, they tend to call them hyperspheres. Space, hyperspheres. Okay? So, the area of a d-dimensional hypersphere. We'll start with what we know. Okay? We'll start with the surface area of a 3-dimensional, quote-unquote, hypersphere, which we would, using our notation, label a sub 3, and then that is its radius, p, because we're in momentum space. So here's something I can draw that on a 2-dimensional surface. I've got my 3 momentum axes, px, py, pz, and I'm going to use spherical polar coordinates in momentum space. Right? It doesn't matter what the space is. I can use spherical polar coordinates if I want to. And since I'm finding the surface area of a sphere, I think spherical polar coordinates would probably be the best choice to make. So I want to know how I can calculate. You may have learned this. Okay, that's really weird, because that's something with the fonts loaded on this machine, because it does not look like that on my computer in my office. Okay? But that just means p with an arrow on top, right? The magnitude of the momentum is what the symbol p by itself means. What we're going to do is we're going to get the surface area of this. You may have seen this in Math 210, I don't know. Did you figure out how to calculate the surface area of a sphere using integration? That's what we're going to do. We're going to break up the surface area of a sphere into an infinite number of smaller parts, find the surface area for each part, and add them all up. And the shape that makes the most sense for the parts is a ribbon that encircles the sphere like a region of latitude. Okay? And I've drawn one right here. It goes all the way around. It's a little bit above what you might call the equator. Okay? And it is described by a radius p all the way out to the surface. Well, a distance out to the surface. All right? By a polar angle theta, which is the angle that that radial line makes with this, the polar axis, which we choose for the z-axis, pz. Okay? And so I've got this ribbon, or strip, that goes all the way around. And since it's got an infinitesimal thickness this way, which, by the way, is just p times an infinitesimal increment in the angle theta, that's this width this way, okay? Then the area of this ribbon is pretty easy to write down. It's the circumference, 2 times pi times the actual radius of this ribbon, which would be from here perpendicularly over to this pz axis. 2 times pi times the radius is the circumference, times that width. Well, the radius of this loop, the perpendicular distance from this point over to the z-axis, is p sine theta. So the area of that ribbon or loop is 2 times pi times p sine theta times p d theta. And that's the area of that one loop. I'll note, by the way, that the thing I put inside this box here, which is just 2 times pi times a radius of a loop, you could call that the surface area of a two-dimensional hypersphere. I.e., a two-dimensional hypersphere is a circle, and the surface area of a circle is its circumference. We're generalizing these words, all right? And so if we think of that thing beside the box as the surface area of a two-dimensional hypersphere, using our notation it'd be A2, and the radius is p sine theta. So the way we get the surface area of the three-sphere, a momentum p, is we take the surface area of this arbitrary two-sphere, this loop, with radius p sine theta, times p d theta, that's this width of the loop, and then we add all these up, because there's a whole bunch of loops from that point all the way down, wrapping around the sphere, down to the bottom point. Just think of a bunch of stacked loops from the top pole to the bottom pole. Okay? And just add up all the areas of all the loops. Well, of course, that's an integral. And I'm integrating with respect to theta, because that's the variable that keeps track of the loops. Theta can go from 0, that'll be the top point, down to here, that'd be pi over 2, down to the bottom point, that'd be pi. So theta is integrated between 0 and pi. Pulling constants out front, as I work my way down, all right, the distance from the center out to the surface is the little p, that's constant. But there's a factor of sine theta, d theta, that has to be integrated. And that just gives you a 2. With that 2 from the integral and the 2 pi p squared out front, you get 4 pi p squared. 4 pi times the radius squared. Proved, right? You derived that result. Now I'm going to make a big, big leap. And I'm not really proving it, I'm just claiming it. Okay? If you want to see a proof, you can look in the appendix in your book. But here's what I'm going to do. I'm going to write the factor in front of the p squared. I already knew, by the way, that the surface area of a three-sphere would go like p squared. Surface area goes like the dimensionality of the sphere minus 1. Okay? So I already knew it was going to go like p squared. What I didn't know was what the constant was in front of p squared. And for the three-sphere, it's 4 pi. So let me take the 4 pi from the case of the three-sphere and write it in a really, really wacky way. I'm going to write 4 pi as 2 pi to the 3/2 over the gamma function, where the argument of the gamma function is 3/2. The gamma function is related to the factorial function that we talked about. If you want to read more about the gamma function, that's also in the mathematical appendix in your book. Or just go to Wikipedia and look up the gamma function. Tons of information. All right, now I will just tell you, and in a minute I'll give you how to calculate the value of the gamma function when you have an odd half integral argument like this. But for gamma of 3/2, the output is simply the square root of pi over 2. Now when you look at that, look at it carefully, you can convince yourself that that is 4 pi. So I have written 4 pi in a really wacky way. Okay? 2 pi to 3/2 over the gamma function with the argument of 3/2. Because now, this is where I make the leap. I claim, right now my dimensionality is 3, but let me just use the symbol d for the dimensionality of the hypersphere. And I claim that the constant that's going to be part of my surface area is going to be 2 pi to the d over 2 gamma function of d over 2. And if I just make that claim, then I have this result. for the surface area of a d-dimensional hypersphere. Okay? 2 times pi to the d over 2 over the gamma function with an argument of d over 2, all multiplying the radius of the hypersphere to the d minus 1 power. So we've got to check that for a couple of cases. Like the 2-dimensional hypersphere is a circle of a given radius p, and the surface area of a circle is its circumference. 2 times pi times the radius. Let's make sure that comes out of this formula we just wrote. So we put in d equals d equals 2. So we have 2 pi to the 2 over 2 gamma with an argument of 2 over 2 p to the 2 minus 1. So that's 2 pi over a gamma function of 1 p to the 1. The gamma function of 1, you can look that up. It's 1. So I've got a 2 pi over 1 times p, which is 2 pi p. You can check that for the 3 hypersphere, you plug in d equals 3 here, here, and here, and you get 4 pi p squared. Okay? How about let's do one more? How about a 4-dimensional hypersphere of radius p? What's the surface area of that? 2 pi to the 4 over 2, gamma function of 4 over 2, p to the 4 minus 1. That's 2 pi squared, gamma function of 2, p cubed. Here's a really helpful thing to remember. The gamma function of n, if n is an integer, is n minus 1 factorial. Okay? Really helpful to know that. The gamma function of n, if n is an integer, positive integer, is n minus 1 factorial. So gamma function of 2 is 2 minus 1 factorial, which is 1 factorial, which is 1. Okay? So I've really just got 2 pi squared times p cubed. 2 pi squared times p cubed. Well, you can keep going, yes? You can figure out the dimensionality of any size, any dimension, hypersphere. I will give you one more useful result. What is the gamma function of an integer plus a half? Okay? I said m. M plus a half, where m is 1, 2, 3, dot, dot, dot. It's rather interesting looking result. I'm just stating without proof. 1 times 3 times 5, so we're multiplying odd integers out to a maximum of 2m minus 1. So how far you go up here depends upon what the m is. Divided by 2 to the m, square root of pi. So those are results we're just going to take and use, and of course we're just going to take and use this. Okay? So that's what I'm going to do. I'm going to use that, because what do I have over here for my case with 2 atoms in the box, with a specified total energy for the 2 together, capital U. Well, I got down to the point where I needed, at least for the volume and momentum space part of the multiplicity, I needed to know the surface area of a hyper 6 sphere. Okay? And now use that result. Okay? So, using the PowerPoint slide, we have A sub 6 for a sphere of momentum p is 2 pi to the d over 2, d is 6, 6 divided by 2 is 3, so 2 pi cubed, over the gamma function with its argument d over 2, again d is 6, 6 over 2 is 3, so the gamma function of 3, times the radius, which happens to be p, to the d minus 1, so p to the 5. So this is 2 pi cubed in the numerator. Remember, one of the nice properties of the gamma function is that if the argument is a positive integer, such as here, the gamma function of a positive integer is 1 minus that integer factorial. So gamma of 3 is 2 factorial times p to the 5th. But of course 2 factorial is 2. That will cancel the 2 in the numerator. So I just end up with pi cubed p to the 5th. next bulleted step, let's write down the multiplicity for a 2-atom system with volume in position space, V, and total energy, U. It will be. So I'm basing this on my extension of equation 2. Remember, the volume in position space has now been raised to the power of 2 because I have 2 particles and they each have the volume V. I have, because of the uncertainty principle, a factor of h bar over 2 to the 6th power. Okay. Times the volume in momentum space. So that's a sub 6 of p delta p, right? That's the volume in momentum space. So that's v squared pi cubed p to the 5th delta p over h bar over 2 to the 6th. It turns out there is a subtle caveat we have to put on this result. Okay? It turns out that for a quote-unquote gas of 2 identical particles, we have overcounted the multiplicity by a factor, in this case, of 2. Why is that? Because if I imagine that being the box in position space that's available, that if I have a state where one of the atoms, we'll label it 1, and the other atom, labeled 2, is in a certain location and has a certain momentum, something like that. If I were to merely switch the particles, but not change the positions or the momenta, so same positions, same momenta, but switch the labels, okay? You can't tell those 2 microstates apart in quantum mechanics, okay? You cannot tell those apart. That's what identical means, right? You cannot distinguish between these 2 microstates. Okay? And it turns out that this counting, where I just go like v squared and h bar over 2 to the 6, all that includes both of these in the counting. Okay? So in order to get the counting right, you have to divide our expression omega sub 2 by a 2. Okay? This is not, by the way, at all immediately obvious that you have to do this. This was one of the things that confounded people in the early days of statistical mechanics, this counting, because for reasons later on, when they were doing certain calculations, things weren't adding up right. Okay? And they had to go back and they had to rethink about what they were doing. And Gibbs was the name of the person who figured out that things were being overcounted. Okay? Alright, so the corrected multiplicity for the 2-atom gas, I'll just still use the notation omega sub 2, but I'll now write it in the corrected form, is v squared pi cubed p to the 5th delta p over 2 times h bar over 2 to the 6th. All right, now here we go. From 1 atom in a box to 2 atoms in a box to n atoms in a box. Okay? So now we're going to generalize to a gas of capital N identical particles. And we're just going to write down the multiplicity, okay? But now we're going to label the macro state by the number of particles, the volume and position space, and the total energy of all the atoms in the gas. But we still use the symbol U for that. All right, let's see if we can generalize from what we did in the 2-atom case. What do you think the volume term becomes if you have N particles? V to the N. Okay, that's an easy one. V to the N. This thing right here, remember, well, it is, maybe a more careful way to write that is a VP2 for 2 particles, right? It's the volume in momentum space for 2 particles. So I need what is the correct volume in momentum space for N particles, okay? Now the way I wrote that is I wrote it like that. Because why? Because I ended up with a 6 sphere, remember? In momentum space. With 2 particles, I had a 6 sphere. With each particle, I get 3 more dimensions in momentum space, right? With each particle, I get 3 more dimensions in momentum space. So the V in momentum space, I'm going to label with a 3n and radius P. Okay? Then downstairs, I have an h bar over 2. Notice in the 2-atom case, I had a 6 here. So what do you think the power will be in the N atom? 3n. Now here comes the tricky one. What do you think the 2 becomes? Well, I got a lot more than 2 particles now. You might think n, right? But it's n factorial. Because what it really is the number of ways that you can swap the particles, right? So, for example, try it yourself with, instead of a box with 2 atoms, try it with 3. And put labels, and just make copies, and just switch pairs of labels. And how many different ways can you do it? And the answer is, if there are 3 particles, that there are 6 ways you can do it, which is 3 factorial. Okay? So you have to divide by an n factorial. Okay? And that's the number of permutations. The number of permutations of the labels of the particles. That's what the n factorial is. Let me also note that the volume in momentum space will be of a 3n sphere, okay? And that will have a surface area, A3n of P times a delta P. Because it's still just a spherical shell with some surface area and some little bit of width. You just can't imagine it now, right? You can't visualize it. Because you're in 3n dimensions, and n by itself is a large number. Okay? So now, we're almost at the final result. So now, multiplicity for a macro state specified by those 3 quantities, in atoms, volume V in a box, total energy U, is, okay, I'll just do some grouping. 1 over n factorial, V to the n, h bar over 2 to the 3n, okay, times. I need the surface area of a 3n sphere with radius P. So I just go to that, and for the dimensionality, I put in 3n. Okay? So that's going to be 2 pi to the 3n over 2 over a gamma function of argument 3n over 2 times p, all right, to the dimensionality minus 1, so that would be 3n minus 1 times delta p, right? You see what I did? I don't want to do all this work and then lose you at this point. I don't want it to be mysterious where this result comes from. Does everybody see what I did? This part right here is the surface area of a hypersphere of dimensionality 3n. Okay? All right, but remember that the radius of this hypersphere squared is 2 times m times the total energy. So, the radius to the 1 power is the square root of 2 times the mass times the total energy. And the radius to the 3n minus 1, because that's the factor I've got in the multiplicity function, p to the 3n minus 1 means 2mu to the power of 3n minus 1. That's what's going to end up being part of what's up here, right? I'm getting ready to put that in here. Okay? But I've expressed it, remember this is the radius, this p is the radius of this hypersphere. And the radius of the hypersphere is proportional to the total energy. Remember my two-dimensional case there? Okay. All right? Yes, that should be divided by 2. Thank you. Very good. Very good. That's right. Keep me on track. Okay? Because it was 1/2. Yes, absolutely. All right. Good. Next thing. Remember, capital N is going to be a large number. Right? Think Avogadro's number. So, 3n minus 1, oh, for all intents and purposes, that's 3n. Remember, when you add or subtract a regular number from a large number, you can omit the regular number. So I'm going to do that. That means this is going to become 3n over 2. Okay? That's all that means. That's going to become 3n over 2. Now I'm going to do some grouping. I'm going to define a function, I'll just call it f, that's going to depend on the number of atoms. I write that of n. The key thing is that f is not going to depend on the other two macroscopic properties, volume and total energy. Okay? It's not going to depend on v and u. But it's going to depend on the number of particles. So I'm going to gather terms. Basically, I'm going to gather now and put into this function everything that isn't a v or a u. So there'll be an n factorial downstairs. There'll be an h bar over 2 to the 3n in it. Okay? There'll be the delta p. We'll put that in there. There'll be the 2 pi to the 3n over 2. There'll be the gamma function of 3n over 2. Okay? And I'm going to take a 2m to the 3n over 2 also. Put that in here. Okay? So the f function f of n is defined to be 2 times pi to the 3n over 2 power times 2m to the quantity 3n over 2 power. If you want, I guess you could put the pi inside that parentheses then with the 2 and the m, since they're both to the 3n over 2 power, times delta p over n factorial h bar over 2 to the 3n power and gamma function of argument 3n over 2. I do all this because it's going to turn out that for the most part, this function f of n is not going to be the most important part of our final answer for the multiplicity. Here's what it's going to look like now, the multiplicity. Here we go. So, final expression. This is as pretty as I can make it. The multiplicity of n identical atoms in an ideal gas is a function that depends on the number of atoms, the mass of the atoms, and this range of momentum values that is imposed upon us by the uncertainty principle, times, okay? How does the multiplicity depend on the volume of the box? Look over there. It's the volume to the n power. And how does it depend on the total energy of the gas? It's the total energy U to the 3n over 2 power. And that's a pretty important result. Okay? So it's a number, we're up to 3. This is a monatomic ideal gas with n identical particles. Notice we have indeed ended up with a very large number for the multiplicity because we have taken regular numbers, v and u, and raised them to the power of large numbers. Okay. Yes?
So the atomic ideal gas would be more complex?
It would be more complex because the total energy, U, would be not just translational kinetic energy, but there could be rotational kinetic energy too. Okay?
This is only for if it's n equals like the operator. Right?
Yeah, large N. Okay. Well, certainly large enough that this is reasonable.
Yeah.
Okay, so, now we're going to end up doing a number of things with this result. Obviously, I wouldn't spend this much time deriving it if it weren't. And the next thing I want to do, I guess I don't really want to just get like wade right into something and then just barely get started and have to stop. So let me just talk briefly about what we're going to do next, and then we'll start this on Thursday. So what I want to do next, I want to take advantage of this result. I'm going to take two ideal gases, put them into contact with each other, and let them exchange energy, but be isolated from everything else. So the total energy of the two together is fixed. But they could exchange energy slowly between them. Okay? Remember I did that kind of thing with two Einstein solids. Okay? You've got a homework problem that's going to do that with two paramagnetic solids. Okay? So I'm going to do it with two ideal gases. And I'm going to show you, yet again, that all you have to worry about is, for that double system, that compound system of two ideal gases, is the macro state with the largest multiplicity. And I'm going to show you that when I plot the multiplicity versus the macro state energy, that it's going to be a Gaussian peak, and it's going to be so narrow that you don't have to worry about anything but the macro state with the largest multiplicity. I'm going to show you how narrow that peak is. Just like I did with the two Einstein solids. Starting to see a pattern? All right? All you got to do is find the macro state with the largest multiplicity. And for any system with an n of the order of Avogadro's number, that is all you have to worry about. So I'm going to show you how that comes out of this result. Okay? And then the last thing we'll do in chapter 2 is we're going to finally, officially, and formally define the concept of entropy. Okay? And that will enable us to rewrite the second law of thermodynamics using that concept of entropy. Okay, but next thing will be to show you that if I put two ideal gases together, let them exchange energy, they will evolve to the macro state with the largest multiplicity, and that is the only state that has any appreciable probability of being observed. Okay? Okay.